The Theory and Design of the Yagi-Uda Array Aerial Presentation Version 2 by Joseph P. Campbell, HNC, Marine Navigational Systems Engineering. Revised 17th of July 2011. Contents: Number 1. History and Development. Number 2. A folded half-wave dipole. Number 3. The Yagi-Uda Array Elementary Principle. Number 4. Effects of additional parasitic elements on the driven element's electrical characteristics. Number 5. Side lobes and computer simulation. Number 6. Parasitic element spacing and aerial gain. Number 7. Yagi-Uda arrays and noise temperature. Contents continued on next slide. Number 8. Stacking and baying Yagi-Uda array aerials. Number 9. Stacking and baying the advantages. Number 10. The Yagi-Uda array, its applications. Number 11. Yagi-Uda array aerial paradigms, parts 1 to 8. Number 12. Synopsis. Number 13. References 1 to 6. And finally number 14. About the author. History and development. During the early 1920s, Professors Yagi and Uda, based at a university in Japan, set about researching and developing a directional aerial for the high frequency, very high frequency, ultra high frequency and the longer wavelength of the super high frequency microwave band, these being centimetric waves longer than about 5 centimeters approximately. Centimetric waves are waves whose wavelengths are most appropriately measured in centimeters. Photo 1 shows Professor Hidetsugu Yagi at work. A folded half-wave dipole. The folded half-wavelength dipole is the elementary aerial that most forms of practical commercially made Yagi-Uda arrays, Yagi aerials that is, are based on, except for ones designed for receiving high-frequency band signals and some two-element VHF designs. This folded dipole will have a feed point impedance of about 300 ohms, if not used in a Yagi aerial arrangement. See Photo 2. The Yagi-Uda Array Elementary Principles. A half-wave dipole has minimal directional properties. Indeed, when it's vertically polarized, it can be considered to be a practical omnidirectional antenna. In order to increase its directionality, we can place a parasitic element behind it of a specified greater length than this dipole and at a specified distance from it with the same polarization. We now have a basic Yagi aerial comprising two elements, as shown in Figure 1 opposite. Addition of a director element. If we just make do with a half-wave dipole and a director element, we won't usually have enough directionality for most of the applications concerning radio frequency and microwave wireless reception and transmission. In order to mitigate the problem, it's possible to add a further parasitic element, but this time in front of our half-wave dipole, the dipole being our driven element, that is to say the point where a feeder cable is connected to our Yagi aerial. See Figure 2 opposite. I must have to say that if you only use a two-element Yagi for an SHF wavelength, it won't be much good, so you'd need to use a multi-element Yagi-Uda array for microwave SHF applications. Reflector and first director element, proportional size to the driven element. Shown in Figure 3 is a schematic representation of a 4-element Yagi-Uda array aerial. In such a design of aerial, the reflector element is 5% longer than the driven element, this being a folded half-wave dipole of impedance 300 ohms. The first director element is 5% shorter than the driven element, and subsequent director elements decrease in a certain ratio. The greater the number of parasitic director elements attached to the Yagi in question's boom, the lower the impedance value drops at the feed point to the folded dipole driven element. Yagi array aerials, further principles. The parasitic elements of the Yagi aerial operate by re-radiating their signals in a slightly different phase to that of the driven element. In this way, the signal is reinforced in some directions and cancelled out in others. It's found that the amplitude and phase of the current that's induced in the parasitic elements is dependent upon their length and the spacing between them, and the dipole or driven element as it's known. Yagi array aerials, further principles, part 2. Using a parasitic element, it's not possible to have complete control over both the amplitude and phase of the currents in all the elements. This means that it's not possible to obtain complete cancellation in one direction. Nevertheless, it's still possible to obtain a high level of gain in addition to having a high degree of cancellation in another in order to provide a good front-to-back ratio and also a good front-to-rear ratio. Yagi array aerials, further principles, part 3. To obtain the required phase shift, an element can be made either inductive or capacitive. If the parasitic element is made inductive, it's found that the induced currents are in such a phase that they reflect the power away from the parasitic element. This causes the Yagi aerial to radiate more power away from it. An element that does this is called a reflector. Yagi array aerials, further principles, part 4. It can be made inductive by tuning it below resonance. This can be done by physically adding some inductance to the element in the form of a coil, known as a loading coil, or more commonly by making it longer than the resonant length. Generally, it's made about 5% longer than the driven element. If the parasitic element is made capacitive, it will be found that the induced currents are in such a phase that they direct the power radiated by a parasitic element in the direction of the aerial's remaining ones. An element which does this is called a director. Yagi array aerials, further principles, part 5. A parasitic director can be made capacitive by tuning it above resonance, i.e. above its resonant frequency value. This can be done by physically adding some capacitance to the element in the form of a capacitor, or more commonly by making it about 5% shorter than the driven element. It's found that the addition of further directors increases the directivity of the aerial, increasing the gain and reducing the beam width. That's the beam width of the main lobe of the Yagi in question. The addition of further directors makes no noticeable difference above a certain number for a Yagi aerial designed for a particular radio frequency or SHF subband allocation, such as C-band, L-band, S-band, etc. Effects of additional parasitic elements on the driven element's electrical characteristics. With the addition of a reflector parasitic element, the impedance, denoted by the uppercase letter Z at the cable feed point of the half-wave dipole acting as the driven element, decreases. Adding a further parasitic element, this time in front of the driven element and known as a director, decreases this impedance further. In fact, the greater the number of parasitic directors placed in front of the driven element, the smaller the value of impedance at the Yagi aerial's feed point. Effects of additional parasitic elements continued. This phenomenon has implications concerning the correct impedance matching to the 50 ohm or 75 ohm coaxial feeder cable that the aerial at issue is connected to. In order to circumvent this problem, the driven element is a folded half-wave dipole. Such a dipole on its own has a feed point impedance of about 300 ohms. The addition of parasitic elements brings this impedance value down to approximately the value of the coaxial feeder that's appropriate for the receiving or transmission system in question. The spacing distance between the driven element and the parasitic elements will also affect the value of impedance at the half-wave dipole's feed point. Half-wave dipole, 2-element and 3-element Yagi-Uda arrays, all horizontally polarized. Directional characteristics, i.e. radiation plots. Figure 4 shows the radiation plot for a horizontally polarized half-wave dipole. If it was vertically polarized, the dipole in question, it would be essentially an omnidirectional antenna. Figure 5 shows the polar plot for a 2-element Yagi aerial for a VHF frequency allocation. Note the decreased size of the rear lobe and the narrower main lobe, or it should look narrow, but there's a difference in scaling between these three polar diagrams. Consequently, figure 6, which shows the polar plot of a 3-element Yagi for another VHF allocation, It should actually show the main lobe being narrower than the one in figure 5 and figure 4, but it doesn't because the scaling is different on the polar diagram graticule in question. It does, however, show the considerably decreased rear and back lobes of the 3-element Yagi aerial plotted issue. Side lobes and computer simulation. Depending on the spacing of the parasitic reflector and director elements, a Yagi aerial will display side lobes to a greater or lesser extent. The spacing distance will also determine the front to back ratio and also the front to rear ratio, which is a slightly different parameter, and therefore the size and number of rear lobes present at the aerial. Figure 7 shows a radiation plot that's been output from a computer aerial design and simulation software application for a 2 meter 9-element Yagi-Uda array with a gain of 16.3 decibels relative to an isotropic radiator. An isotropic radiator being a theoretically perfect omnidirectional antenna. Side lobes and computer simulation continued. A homemade, that's home brewed in amateur wireless parlance, Yagi aerial will nearly always display a greater number of side lobes and ones that are more pronounced than an aerial for the same frequency allocation which is commercially made. This is shown in photo 3 on the top of the chimney stack in the image at issue. Side lobes and computer simulation continued too. Manufacturers have access to state-of-the-art aerial design simulation computer software applications that outputs the optimal parasitic element spacings for a Yagi aerial given the required RF or microwave wireless bandwidth and gain characteristics that are input into the computer in question concerning a particular band in addition to the diameter of the driven and parasitic elements. Note, there's a restriction imposed by Ofcom on diameter concerning transmitting uses, subject to the maximum range permitted for the particular RF or microwave wireless system at issue. The significance of the diameter of a driven element of a Yagi aerial and the associated director and parasitic elements is that the wider the diameter of the elements comprising a Yagi aerial, the more power the Yagi aerial in question can dissipate and radiate. In other words, you can put more power into a Yagi aerial with wider diameter of aerial elements and driven elements that you can with a Yagi aerial for the same frequency allocation with shorter diameter driven element and associated reflectors and directors. Parasitic element spacing and aerial gain. As I've outlined, the spacing of the parasitic elements determines the number, size and position of the side lobes of a Yagi aerial. Thus, parasitic element spacing is a major factor in determining the aerial's gain at a given frequency within its bandwidth, as well as, of course, the number of elements comprising it and the impedance value at the Yagi aerial's driven element feed point. Figure 8 shows a graph showing the plot of the power transmitted by a Yagi-Uda array aerial for a given spacing value of parasitic director element expressed in fractions of a wavelength above and below the full wavelength of a given aerial's resonant frequency. Parasitic spacing and aerial gain continued. Because of the reciprocity theory concerning a given aerial used for transmitting or receiving or both, the radiation plot of it will be identical for both types of operation, and so therefore Figure 9 will have a very similar graphical form to Figure 8. Figure 8 shows a graphical plot of received current in microamperes against parasitic element spacing expressed as fractions of a wavelength above and below the full wavelength of the resonant frequency of the given Yagi-Uda aerial featured in Figure 10 previously. Yagi-Uda arrays and noise temperature. As illustrated in Figure 10, the greater the size of the side and rear lobes of the Yagi aerial in question, the greater the pickup of unwanted electromagnetic noise, and therefore the greater the value of noise temperature present in it. Figure 10 shows the effect of side lobes and rear lobes on the noise temperature value present in a Yagi aerial, and therefore output from it. Part A of the diagram in figure 10 shows a Yagi orientated towards a cold radio sky with a noise temperature of 200 Kelvin. Thus the antenna noise value output from it is 200 Kelvin. In part B of the figure 10 diagram, the Yagi concerned has side or rear lobes that are 20 decibels down from the main lobe of the Yagi in question, the Yagi being orientated towards a radio cold sky of 200 Kelvin. The warm ground at the back of the Yagi being of a noise temperature of 1000 Kelvin. Now, because the side and rear lobes are 20 decibels below the main lobe, the total noise temperature output from this imaginary Yagi-Uda array aerial will be 200 Kelvin, that's received from its main lobe, plus 20 decibels down from 1000 Kelvin, and 20 decibels below 1000 Kelvin is 10 Kelvin. Therefore the total antenna noise temperature will be 200 Kelvin plus 10 Kelvin, which will equal 210 Kelvin. Yagi-Uda arrays and noise temperature continued. One of the objects in avoiding a large number of side lobes, and of the one left minimizing their size at the design stage, is to avoid receiving more free space propagated electromagnetic noise than is absolutely necessary. Such noise generators include the atmosphere, solar and galactic sources, for example the Milky Way, the galaxy where our solar system resides. See figure 11. Figure 11 shows the factors contributing to the noise temperature at a receiving aerial. The natural sources of sky noise include cosmic noise, which is essentially radio frequency noise emitted from star and interstellar matter being very large clouds of dust that are emitting radio frequencies. These very large clouds of dust may eventually collapse and form a star millions of years into the future. Cosmic noise decreases with frequency and is negligible above 1 gigahertz. So, as I said, cosmic noise is essentially radio frequency noise. The official start of the microwave spectrum in the United Kingdom is 1 gigahertz. So therefore cosmic noise has only very low amplitude microwave components. Certain parts of the sky have hot sources, so avoid pointing your Yagi-Uda array or indeed any other form of directional aerial if it's going to be used for communication purposes. Avoid pointing it towards the sun, where it could increase the noise temperature in the Yagi, subject to the gain of the Yagi, by maybe 12,000 Kelvin. If you orientate your communications Yagi aerial towards the moon, or the moon happens to be low in the sky and it's within its main beam, it could increase the received noise level by 200 to 300 Kelvin, subject to the gain of the Yagi-Uda array aerial in question. Of course, the moon could actually be away from the main lobe of the antenna. If you're using a low-quality Yagi-Uda array with significant side lobes or a large rear lobe, depending on the position of the moon in the sky, it could hit one of those significant lobes and increase the noise level by 200 to 300 Kelvin. The propagation medium may contain clouds, it may be raining. Water vapour and rain will output a microwave emission, and with high gain Yagis they're detectable and will increase the noise level output from your Yagi-Uda array aerial significantly. Stacking and baying Yagi-Uda arrays. A method of increasing the directionality over that present with one Yagi aerial is to use two or more Yagi aerials mounted vertically above one another and separated by a specified number of wavelengths. That's in accordance with proven aerial theory. This technique is known as stacking. For a practical example of two stacked Yagis, see slide 29. Stacking and baying the advantages. If you stack two identically polarized Yagi aerials correctly, and therefore in accordance with proven aerial theory, you'll decrease the vertical beam width available when compared to using only one Yagi aerial. That is to say, you'll have a more directional aerial arrangement in the vertical plane. See Figure 12. For a practical example, see Slide 29, which features the use of two stacked Yagi aerials for a telemetry system. If you bay two identically polarized Yagis correctly, you'll decrease the horizontal beam width available. That is to say, you'll increase the directionality in the horizontal plane. See Figure 13. Stacking and baying and combined stacking and baying are both forms of spatial diversity, receiving and/or transmitting aerial arrangements. Stacking and baying the advantages, Part 2. With both techniques, you must use an electrical circuit known as a combining unit, which combines the output of two or more aerials of interest in phase before sending it down a coaxial feeder cable to an RF or microwave receiver, or, if this arrangement is used for transmitting, feeds the radio frequency or microwave energy into the stacked and/or bayed configuration in phase. Stacking and baying the advantages, Part 3. It's possible to have both a stacked and bayed arrangement using a minimum of 4 Yagi aerials. If you both stack and bay identically polarized Yagis, then you'll decrease the beam width value in both the vertical and horizontal planes in comparison to that available when using only one Yagi aerial, if it's identical to the ones used in the multiple array under discussion. One combining unit is used with a stacked and bayed Yagi aerial arrangement. And note, you have to have all 4 Yagis in a stacked and bayed arrangement of 4 Yagis orientated with the same polarization. If you have, say, one Yagi vertically polarized and the other 3 horizontally polarized, or 2 of them vertically polarized and the other 2 in the stacked and bayed arrangement, the reverse polarization, you'll cause an impedance mismatch and you'll lose signal level. In other words, you'll make such a stacked and bayed arrangement useless. You have to have all the Yagis vertically polarized or have them all horizontally polarized for maximum signal level to be output from a stacked and bayed arrangement of Yagi aerials. Stacked and bayed Yagi-Uda array aerials schematic diagrams. Figure 12 shows a stacked arrangement of 2 Yagi aerials, whilst Figure 13 shows 2 Yagi aerials in a bayed arrangement. It's possible for some applications to use a greater number of Yagi aerials in a stacked or bayed formation. Additionally, it's possible to have a stacked and bayed arrangement of 4 or more Yagi aerials, or indeed some other forms of aerial, for example parabolic dish designs. Stacking Yagi-Uda arrays, practical application, example. Photo 4 shows a stacked arrangement of 2 12-element Yagi-Uda arrays, vertically polarized, and dimensioned for UHF telemetry frequency allocation somewhere between 300 MHz and 420 MHz. The telemetry signals they're transmitting are various operational parameters which concern the functioning of a remote water utility covered surface reservoir that's located outside the town of Moffat in Dumfries and Galloway, Scotland. This stacked arrangement of 2 12-element Yagis is shown in Photo 4 opposite. The receiving site for these telemetry transmissions being located some distance away. Note the solar panels, a form of photovoltaic system at the base of the stacked aerial support stalk, that are used to generate direct current electrical power for this transmission-receiving arrangement. You can also mount 2 identical Yagis side by side and spaced by the optimal number of wavelengths apart, this technique being known as baying. The Yagi-Uda array aerial, its applications. Number 1. VHF and UHF broadcast television and VHF radio reception. Note, in the UK, no broadcast terrestrial television services use VHF. VHF terrestrial television broadcasting systems are used in the United States and some other parts of the world, but not in the UK. There are, however, radio amateur slow scan television services that utilize radio amateur allocations on VHF for slow scan television and even faster scan television. Number 2, low-power UHF studio transmitter links that are licensed by the Office of Communications for use with restricted service license temporary radio broadcasters such as those organised by college, university, voluntary or religious groups. Number 3, VHF and UHF wireless telemetry systems used in public utilities concerning electricity, gas and water supply installations. However, quite often such installations usually utilise a BT PLC lease line, private wire or private circuit to convey what are effectively telemetry readings. They may also have a full wireless telemetry system there in parallel in case the landline system fails. The Yagi-Uda array aerial, its applications continued. Number 4, emergency embassy HF radio communication systems using skywave propagation that are used in the event of their low Earth orbit satellite communications, known as SATCOMs, and which use microwaves failing. Number 5, military HF, VHF and UHF wireless telemetry and other communication systems. Its applications continued. Number 6, amateur wireless operations covering the radio frequency band starting at approximately 12 MHz and going up to the super high frequency microwave amateur band allocations below about 6.2 GHz, which is longer than about 4.84 centimeters in wavelength. If you try to manufacture a Yagi-Uda array aerial for frequencies shorter than 4.84 centimeters approximately, you'll find the aerial aperture is too small for the Yagi principle to work properly. So you don't usually build Yagi aerials to receive wavelengths shorter than approximately 4.84 centimeters, which means you don't usually go above 6.2 gigahertz. The Yagi-Uda array aerial, its applications continued. 3. Number 7. As part of a stacked and bayed spatial-diversity receiving arrangement comprising 4 Yagi-Uda arrays for the reception of low field strength SHF microwave wireless transmissions, sometimes known as centimetric waves, that lie above 3.2 GHz, equating to a wavelength of about 9.3 centimeters, but below about 6.2 GHz, which, as I've said, equates to wavelengths longer than about 4.84 centimeters. In addition to providing increased signal gain, combined stacking and baying of identical Yagi-Uda array aerials provides an increased bandwidth and combats multiple path propagation, known as multipath, effectively in comparison to using only one Yagi-Uda array aerial. The Yagi-Uda array aerial, its applications continued. 4. These microwave emissions that have been referred to can suffer from multipath propagation difficulties because of their very short wavelengths of the order of centimeters, and so more than one Yagi-Uda array aerial may be needed in order to provide more directionality and so remedy this problem, which would cause phase addition and phase cancellation of the received signals. You want a more directional aerial to eliminate the so-called multiple path and just focus on the direct path from the transmission site. UHF broadcast television channel numbers and how they equate to aerial group letters and colours, as shown in figure 14. Channels 21 to 37 are covered by aerial group A, which is colour-coded red, which means a Yagi-Uda array aerial for this part of the UHF spectrum will have a red plastic bung at the end of the aerial's boom to denote group A. Channels 21 to 27 constitute UHF band 4. Channels 35 to 53 inclusive are covered by aerial group B. That's the middle portion of the UHF band 4 and band 5 spectrum. There's an overlap between the top of UHF band 4 and the lower channel numbers of UHF band 5. That's covered by aerial group B, colour-coded yellow. And the top, I would say the top 2/3 of UHF band 5 are covered by aerial group CD, colour-coded green, which means that if you purchase a Yagi aerial for the aerial group CD channel allocations, you'll see a green plastic bung on the end of the aerial's boom. They don't usually show aerial group letters on the aerials concerned because they'll be worn off because of the weather elements over the years. The top 2/3 of the UHF terrestrial television analog spectrum can be covered by aerial group E. you'd use aerial group E and not aerial group CD if the channel spacing exceeded the bandwidth allocation for aerial group CD aerials. If your channel spacing exceeded that for aerial group A, you'd usually resort to an aerial group K aerial, which goes from channel 21 to 48, which includes therefore an extra 11 channels of coverage in comparison to aerial group A. In some parts of the country, UHF channels are allocated to transmitters which are spread across both UHF band 4 and 5 and widely for one or two transmitters, and that's because of frequency planning measures due to interference from transmitters in neighbouring regions sometimes, and they need to put the DTT in the remaining analog channels if they are being transmitted from a site in question spaced right across UHF band 4 and 5, which is where group W, that's wideband Yagi aerials, come into play. It's not advisable to use group W aerials all the time, because if you purchase a Yagi aerial with a very wide bandwidth, which group W aerials are, you're going to sacrifice the gain value of the gain value that you would prefer to have. You'll have a lower gain because of an increased bandwidth you want, because gain multiplied by bandwidth is a constant known as the gain bandwidth constant. So it's only advisable to use aerial group W as a last resort. UHF band 4 and 5 TV broadcast channel numbers. Figure 14 shows a chart equating to UHF band 4 channel numbers to their respective carrier frequencies, vision carrier frequency only, if considered in the context of PAL analog TV channels. The associated analog monophonic channels are 6 MHz above the stated channel number vision carrier frequencies as listed in the right-hand column of figure 14 and 15. In the case of the NICAM 728 digital subcarrier signal, that's 6.552 MHz above the stated vision carrier for any given channel number on UHF band 4 or 5. Figure 15 shows the UHF band 5 channel numbers and the carrier frequencies they equate to. Thus, a Yagi aerial suitable for receiving group A channels will have elements many centimetres longer than group CD Yagi aerials, aerial group CD covering reception of the highest band 5 frequencies and therefore the shortest of the UHF terrestrial television frequencies concerning wavelength. Aerial group gain versus channel frequency. Figure 15 shows a gain displaying curves that show UHF band 4 and 5 Yagi aerial group gain in decibels relative to a dipole's gain versus UHF channel frequency, displayed on the graph as a channel number. This graph shows why it's not good practice to always install a wideband Yagi aerial, that's group W colour-coded black aerials, to receive any arrangement of UHF television channel groups. That is to say, in order to ensure maximum signal level across a broadcast TV receiver's aerial circuit, you should select a Yagi aerial that just covers the channel frequency numbers required to be received, and it's borne out by the curves shown on the graph in figure 15. So according to this graph, group A, B and CD aerials offer the highest gain but the narrowest bandwidth available, whilst group K, E and W aerials offer a wider bandwidth available to be received and a greater number of channel numbers therefore that can be received, but it's at the disadvantage of outputting a lower signal level across the aerial circuit of your television set concerned. So you should always try to use group A, group B or group CD aerials if your channel spacing from the transmitter you're trying to receive television pictures from permits it. In some areas of the country, channel spacing has to be wider and group A, B or CD aerials can't be used because of interference problems from transmitters in adjacent television regions or within your own television region in some cases, and the frequency planners who are providing the transmission facilities for the ITV companies and for the BBC have to space the channel numbers out further than what would be desirable for using Group A, B or CD aerials, which means that you'll have to resort to using either Group K, Group E, and in a small number of areas in the country, Group W aerials. Group W aerials are aerials to avoid if possible, and you should only use them if absolutely necessary, because if you use Group W aerials in an area where you could just use a Group A aerial, you're going to get a reduced signal voltage across the aerial circuit of your television, because you've paid for an aerial with a much wider bandwidth, which means the gain of the aerial must drop to keep the equation balanced, that is the gain bandwidth product equation balanced. So as you increase gain, you'll decrease bandwidth to keep the value which you get if you multiply those two quantities equal. Gain times bandwidth equals a constant, that is. Looking at the channels that are covered by the various aerial groups, the highest gain aerials, which are Group A, B and CD, cover the least number of channels, whilst Group K, E and W aerials cover a wider number of channels, but it's at the expense, as I say, of offering a reduced gain value and therefore a reduced signal voltage across the aerial circuit of your television set. Additionally, blanket use of Group W aerials will unnecessarily increase the noise temperature across a TV receiver's aerial circuit, which, if the signal strength levels are low, will manifest itself as a fuzzy or fuzzier TV picture than needs to be necessary in the case of the remaining analog PAL TV services being received. You'll usually get away with it in the case of digital terrestrial television reception, but it's not advisable, as in rare cases it could put the received digital TV picture over the digital cliff, and you'll be reduced from either an error-free television signal or one with slight errors to a blank screen. Note, the bandwidth of a Yagi-Uda array, as I've said earlier, is inversely proportional to its gain. Yagi-Uda array aerial paradigms. Photo 5 shows a conventional Yagi aerial for installation in high signal strength areas and used for UHF band 4 or 5 broadcast television reception, either for digital terrestrial television, known as DTT, or the remaining analogue television services. Where I live in Wirral, Merseyside, northwest England, I view my digital terrestrial television services via a horizontally polarised aerial group CD Yagi aerial, which is orientated towards the Winter Hill main transmission mast. It's true to say that virtually all high-power main television UHF transmitter stations in the UK radiate their transmissions in the horizontal plane, whilst virtually all relay transmitters in any given main station transmitter group radiate their transmissions vertically polarised. This is because vertically polarised transmissions carry proportionally further than a comparable horizontally polarised transmission, because from main stations you don't want the signal from the main station to go too far, so you make sure that the transmission concerned is horizontally polarised. For low power relays, you generally want them to give good coverage in an area, so you'll make the transmission vertically polarised, and it won't matter if it carries a little bit further than it should do because it's a low power transmission. Photo 6 shows a higher gain form of Yagi aerial, once known as an X-beam Yagi, again used for UHF broadcast television reception, but in low field strength areas, and still in production today. It's pictured in Photo 6 horizontally polarised, that is to say, its aerial elements are in the horizontal plane, which refers to the pickup of the electric field component of an electromagnetic wave. Yagi-Uda aerial paradigms, Part 2. Figure 12 shows a two-element array for the digital radio age. Its dimension for the reception of VHF band 3 DAB transmissions located on the VHF spectrum spanning 217.5 to 230 MHz in high to moderate signal strength areas. Note, it's only part of the VHF band 3 spectrum that's reserved for DAB in the United Kingdom and elsewhere. There are other services on VHF band 3 not related to DAB or any other form of broadcasting. The length of the driven element, and therefore the director element, will be shorter than those of a 2-element Yagi aerial for VHF band 2, that's analog FM radio reception. Figure 13 shows a 3-element array for DAB reception in moderate signal strength areas. Yagi-Uda aerial paradigms part 3. Figure 14 shows a 4-element array for DAB VHF band 3 radio reception in low signal strength areas, i.e. those areas just outside the official coverage area of the transmitter concerned or screened by foliage. Note, foliage attenuates RF at VHF and above noticeably. This effect increases with the shortening of wavelength and therefore with increasing frequency, wavelength being inversely proportional to frequency. Wet foliage has an even greater attenuation and signal reflection effect, leading to higher field strength and multiple path propagation. Figure 15 shows a 6-element array for DAB radio reception in lower signal strength areas, i.e. a significant distance away from the periphery of a specified transmitter's coverage area. Note, a broadcast transmitter's coverage area is defined in terms of a minimum electric field strength value that's to be received if a particular area is to be described as being within its service area. The subunit of field strength used here is the microvolt per meter, the SI unit of field strength being the volt per meter, but the volt per meter is too large a unit to use in the context of television radio reception, aerial installation and engineering, other forms of engineering, so a subunit, a smaller subunit is used known as the microvolt per meter. Yagi-Uda aerial paradigms part 4. Photo 7 shows top a 10-element Yagi-Uda array aerial for high field strength UHF band 5 DTT areas, and originally used for PAL analog TV reception and located at my address in Wirral, UK. Below it, on the same stalk, is a VHF band 2 3-element Yagi aerial for moderate field strength reception of BBC National Analog FM radio services from the Home Moss radio transmitter near Leeds, West Yorkshire, which serves most of northern England. Below the BBC National Radio VHF FM aerial system, and officially irradiating an effective radiated power of 250 kilowatts, is located BBC Radio Leeds' mixed polarization transmission aerial for their 92.4 MHz VHF FM service, officially radiating an effective radiated power of 5.6 kilowatts. At my home on the Wirral Peninsula, I can receive this transmission most of the time perfectly if I switch my hi-fi tuner from its stereo receiving mode to its mono receiving mode. This drastically reduces the background hiss reproduced on my hi-fi system's loudspeakers, because of the fact that in order to successfully demodulate a monophonic radio transmission, a lower signal-to-noise ratio can be tolerated than is the case with stereophonic reception. Switching the tuner at issue from stereo to mono mode is necessary as I live well outside the official transmitter coverage area for this VHF FM service. That is to say, the signal strength, that's the electric field strength received at my Wirral location, is below the value set by the BBC for adequate FM stereo reception, i.e. below 54 decibels relative to 1 microvolt per meter. This figure equates to an absolute electric field strength value of just over half a millivolt per meter. If I added a further identical VHF band 2 Yagi aerial and combined it with my existing one so as to constitute a stacked arrangement of 2 such Yagis, I would significantly increase the signal voltage presented to the aerial circuit of my hi-fi's tuner component, but this value wouldn't be doubled. However, a cheaper alternative would be to use an active aerial amplifier located in circuit with my band 2 Yagi aerial. This would also provide much higher gain than that which could be achieved using the increased passive gain approach described here. Yagi-Uda aerial paradigms part 5. Photo 8 shows a very similar arrangement to that shown in Photo 7 previously, the difference being in the fact that the UHF band 5 Yagi aerial mounted at the top of the stalk is of a higher gain than that at my address. It has another 7 elements making up this Yagi-Uda array, a total of 17 elements in all. The aerial installer was obviously inferior, as he should have fitted a 10-element array, as this address is located in the same road as mine. At the time this UHF Band 5 aerial was installed, the Winter Hill main television Band 5 transmitter was carrying pan-analog TV, which reached the Lees and Thingwall Wirral at high field strength, i.e. the additional aerial gain over my 10-element Yagi wasn't necessary. However, with the advent of DTT radiated at a considerably lower power, this gain just wouldn't go amiss. It's, therefore, now an appropriate gain figure, though by accident rather than design. Yagi-Uda aerial paradigms, Part 7. Photo 9 shows a Yagi aerial for an amateur wireless frequency allocation below about 6 GHz on the SHF part of the microwave spectrum. Note the very short parasitic elements. Photo 10 shows an 11-element Yagi aerial for the amateur wireless 144 MHz frequency allocation on VHF, which equates to a frequency allocation in wavelength terms of 2 meters. Yagi-Uda aerial paradigms, Part 8. Photo 11 shows, from the top of the stalk, a VHF 2 meter followed by a VHF 4 meter, then a VHF 6 meter Yagi aerial. It's appropriate Yagi-Uda array aerial installation practice to install the shortest wavelength Yagi aerial at the top of the aerial support stalk, a bigger Yagi aerial for a longer wavelength frequency allocation below that specified by a number of centimeters separation to the top Yagi, and the very longest wavelength Yagi at the lowest point, which is practical on the stalk. This is because of wind loading and propagation reasons. Figure 16 shows a 3-element Yagi aerial for the 20-meter wavelength shortwave radio amateur band, equating to a 15 MHz high frequency allocation with traps. A trap is a resonant tuned circuit comprising the electrical components known as an inductor and capacitor, with these traps fitted into each leg of each element of an HF Yagi aerial. The Yagi aerial in question will electrically lengthen or electrically shorten depending on what band of frequencies is fed into it. Synopsis. Number 1. The Yagi-Uda array aerial, known as the Yagi aerial, is a directional aerial, also known as a beam aerial, based on the half-wavelength dipole in a folded form for practical commercially made designs, other than those for the HF band and some 2-element VHF designs. Number 2. The more parasitic director elements a Yagi aerial has, the greater the directionality, i.e. the gain, that the aerial under examination possesses. However, above a certain number of elements for a given frequency band, there are diminishing returns in terms of increasing the received level input into an RF or microwave wireless receiver connected to it. The highest Yagi aerial gain designs that are practical can be engineered for the longer wavelength SHF frequencies, that's longer than 4.84 centimeters in wavelength, that is below 6.2 GHz in frequency. Synopsis continued. Number 3. Yagi aerials have applications in a variety of telecommunications and communications systems in general for public, commercial, industrial, governmental and military users. Number 4. Using the techniques of stacking and baying, it's possible to create very high gain, that is to say highly directional aerial arrangements on the longer wavelength SHF microwave frequencies, and so negating the need for an expensive parabolic dish aerial which, for some applications, may provide an unnecessarily higher gain value. References. Number 1. Radio and RF Engineering Pocket Book, 3rd edition. Authors Steve Winder, Bachelor of Arts, Master of Science, Chartered Engineer, Member of the Institution of Engineering and Technology, Member of the Institution of Electrical and Electronic Engineers, and Joe Carr. First published 1994, 3rd edition 2002 by Nunes, an imprint of Elsevier Science. Number 2. Nunes Telecommunications Pocket Book, 3rd edition. Author Steve Winder. published 2001 by Nunes, an imprint of Butterworth Heinemann. References 2. Number 3. Satellite Communications Link Design, a presentation by Dr. Leila Z. Ribeiro and downloaded via the internet from the website of the George Mason University in PDF form. Number 4. RADCOM, various editions of the Radio Society of Great Britain's journal, including the antennas feature of the June 2008 edition. Author Peter Dodd, call sign Golf 3 Lima Delta Oscar, and the In Practice technical feature of the November 2009 edition, written by Dr. Ian White, call sign Golf Mike 3 Sierra Echo Kilo. References 3. Number 5. The reception advice area of the website for the British Broadcasting Corporation. This area of the BBC's website provides, amongst other technical topics, basic reception advice for broadcast receiving systems using the Yagi aerial, that is to say those receiving UHF band 4 and 5, DTT and analogue channels, DAB radio on VHF band 3, and the analogue FM radio channels located on VHF band 2. References 4. Number 6. The website of the Christian Restricted Service Licensed broadcasting organisation known as Flame Christian and Community Radio, formerly known as Flame FM. Number 7. An informal visit to the Flame FM RSL radio station based at the Wirral Christian Centre in the year 2004. This station transmitted for a number of 2-week periods. References 5. Number 8. The Confederation of Aerial Industries, for information on domestic and commercial TV and radio broadcast reception aerial installation standards. Number 9. The public website of Ofcom, the Office of Communications, this being the independent regulator and competition authority for the UK's communications industries. References 6. Number 10. MaxView, broadcast reception aerial manufacturers. Number 11. Triax, broadcast reception aerial manufacturers. About the author. Joseph P. Campbell. Joseph P. Campbell is 39 years old and is qualified with a BTEC High National Certificate in Marine Navigational Systems Engineering from Liverpool Community College. His HNC was awarded to him in the year 1997. This branch of engineering involves the use of telecommunications and communication systems in general. He's a qualified radio amateur and a member of the Radio Society of Great Britain, his Office of Communications call sign being Golf 7 Oscar Kilo Romeo. He has in the past been active on the 20, 40 and 60 metres shortwave amateur bands. Additionally, he occasionally builds small electronic project kits that require soldering skills to complete. His email address is g7okr@hotmail.co.uk. End of presentation on the theory and design of the Yagi-Uda array aerial presentation version 2. Copyright 2010 Joseph P. Campbell. Revised 17th of July 2011. Thank you for watching.